Dear Barbara, it's an honor and a privilege to have you here with us today as a new honorary doctor of UPM. Let me introduce you to the audience by recording the words of Professor John Buta. Back in 2008, Professor Buta wrote in a letter supporting Barbara's promotion to Institute Professor, the highest title that can be awarded to a faculty member at the Massachusetts Institute of Technology. It's hard to imagine what today programming and distributed systems would be without Barbara's many seminal contributions. Later, when he nominated Professor Liskov to the ACM Turing Award, Professor Bultak noted that dozens of prominent computer scientists from whom he solicited support for that nomination were consistent in that they all say that the work was great, but inconsistent as to which piece of her work they would choose to say was great. And that, he said, and I agree, is a testament of the brief and impact of Liskov's career. So Barbara, thank you very much for the kindness with which you have accepted to give us today this talk about multi-core programming, and thank you all for joining us today.
Thank you very much for that very kind introduction. Right. So today I'm going to talk about work I've been doing recently on multi-core computing. And when multi-cores first came around, and it was maybe 2005, something like that, I can't remember exactly, all of a sudden Moore's law was running out, and so people started to talk about how we needed to have many more processors on a chip so we could get more better performance. And it was perfectly clear that multi-core was great if you happen to have an application that didn't require synchronization, you know, what they call embarrassing parallelism, where every core can be used separately from every other one, and then you get perfect speed up. The big issue is scalability. If I apply a whole bunch of cores to a problem, say 10 cores to a problem, I'd like my program to perform 10 times better than if I ran it on a single processor. And in fact, what people were seeing was you didn't get that kind of speed up, so you weren't really getting that much of an advantage from all those cores for many applications. And I always thought a particularly compelling application was database systems because they underlie almost all the applications that we use today. Now, multi-core machines are kind of distributed, and I've been working in distributed computing for a long time, and they differ from distributed systems in two very important ways. First of all, they share memory, which is absolutely not true in a distributed system. Each computer there has its own memory, and every time you want to look at the memory of some other machine, you have to either send a message over there and have it do the work for you, or you have to physically move the data over to your own machine. That makes the problem harder than distributed computing. How do I get those cores to really share the memory that's there? The other difference is that the cores on a multi-core machine don't fail independently. You can think of that machine as just being something that's either running or it's not. That makes the problem easier. In distributed computing, we worry a lot about how to build systems out of multiple computers where the system as a whole continues to work even though some of the computers are not there. Now, interestingly enough, in that early work on multi-core machines, much of the work took a distributed systems perspective. And the idea was, well, yeah, we got that shared memory, but we don't really know how to use it very well, and it's like distributed computing, so we'll just use it as a message passing technique. And each of the cores ran independently, and they got a little bit better communication because we were using the shared memory for the communication. Really not a very good idea, and clearly not the right way to go. So what happened in around 2000, I'm not sure exactly well, it might have been 2010 or 2011, is that a colleague of mine, Eddie Kohler, you can see his name down at the bottom there, That's Eddie Kohler, Robert Morris, and a student who worked with them. So Eddie's a professor at Harvard, Robert Morris, a professor at MIT, and they developed this system called MassTree. And it showed how to get a really high performance on a key value store. So this is not a database. This is just a system where you could insert a value associated with a key. Later, you could look it up. Each of these was an independent atomic operation, but there was no way of putting them together. And it was really based on shared memory. It was a cache-aware system. And I'm going to tell you a little bit about how it worked. Eddie actually came to talk to me because he wanted to talk about how to reason about the correctness of his code. Like many systems, it had bugs in it. And as time went by, these bugs disappeared little by little. It has this very interesting concurrency control technique. That was why it ran so well. And there were bugs associated with that. And at the time, I was very ignorant about multi-core machines because I've been paying no attention to them. So what I'm going to do today is I'll tell you a little bit about MassTree and then how that work with Eddie progressed. So in a multi-core machine, every core has its own cache. And the memory itself might be organized so that you have better access to some pieces of the memory than others, but I'm just going to focus on the cache. And if you read something into your cache and you want to use it later, things are going to run a lot faster if it stayed in your cache from when you first used it to later on. So this matters for how you organize the use of the machine. Now, MassTree is a tree. So it's just, what you expect out of a tree. It's got a tree structure with interior nodes. And each node covers a range of keys. So it's a technique for looking up a key to find the record associated with the key. And when you finally get down to the record associated with the key, then you'll find the values that you're interested in, which might be complicated things. And the keys, the range of the nodes themselves fall into two categories. Some of them are interior nodes that only point to other nodes of the tree, and then there are the leaf nodes that point to the records. I have a picture of a tree here, which in some sense you should just ignore. There are many kinds of trees, as you know, and actually the technology is kind of independent of what kind of tree you use. In any kind of tree, the kinds of techniques I'm going to describe to you are going to help you with your performance. So the big deal in this system was how they did the concurrency control. And if you think about the history of concurrency control, first of all, originally in the good old days, there were locks. And every program that wanted to share a piece of data would get hold of the lock, use the data, then release the lock. They had what was called a critical section. And then when we got a little bit smarter, and this didn't take too long, we decided there were two kinds of locks. There were writer locks and reader locks. And writer locks were exclusive. So once you had a writer lock, nobody else could use the data. Reader locks allowed multiple readers to use the data at the same time. So the obvious first place to start here is with reader-writer locks. The trouble with reader locks is they have cache effects, because to set that reader lock, you have to modify something. To modify something, this has effect on how the caches work in the machine, and it can often affect not necessarily your own cache, but the caches of other readers who have looked at the same data. So in MassTree, there are no reader locks, there are only write locks. So this is an interesting question because the things that we're locking are numbers of words. So a leaf node of a tree might be 32 words, maybe 16 words. It's some number of words. You probably choose this number of words depending upon the characteristics of the hardware, because hardware brings information into the cache in bunches of words, 8 words, 16 words, something like that. So I already said that. So we're going to have to somehow or other do concurrency control for these units that are multiple copies of words using hardware primitives like compare and swap that work on exactly one word. So how is this going to work? Well, we do something that's very typical in systems like this. We use the first word of a leaf node, a regular node, or a record as a control word. And that word has in it a bit that acts as a lock, and it has a version number that is actually counting how many times that particular record has been modified. So writes are typical in whatever you would do in a system with write locks. You set the lock bit to turn it on, and if it's already set, you have to spin until it becomes available. And there's a lot of issues in here I'm not going to talk about, like, do I spin forever? Do I, spin for a little while and try again? Do I, try for a little while and then stop, and so forth? Doesn't matter for today's talk. But we can set that lockbook using compare and swap. Okay, so now we've got hold of that first word. And then we update the many words that make up the node or the record. And at the end, we then increment the version number and release the lock bit. And that is another compare and swap. So we have a compare and swap at the beginning. That's an efficient hardware instruction, a compare and swap at the end, and in the middle, we're just doing reads or writes. Okay, so that's great for writes, but remember we have no read locks, so how do they work? Well, we first of all start off in a read to see whether the thing is locked. And if it's locked, we spin, with the same issues I mentioned before about do we spin forever and so forth. Once we see that the thing is unlocked, we then read all the words that make up the record, many of them, 16 of them. Now the problem is that while we're reading, some other core might have set the write lock and started to write. And so we might have seen the first 4 words of the record in the old state, and then we get to the 5th word and we see something that's been changed already. And so if we didn't do something special, we would see an inconsistent state, in other words, garbage. Okay, so what we do is after we've read all the words of the record, we go back and we look at the first word of the record to see whether it's the same as it was when we started. And if it's the same, then we feel that everything is okay. And otherwise, we just do the whole thing again. Okay, now I want to point out here that this technique only works for certain hardware semantics. Okay, so the gold standard for hardware is what's called sequential consistency, which means if I write in one cache, it immediately writes through and affects the caches of all the other machines. Hardware designers don't like that because it's efficient to implement. There's something a little weaker called total store order, which says that we don't fuss with all those other caches right away, but if you happen to see something that's been changed, then you will see all the changes that happened before that. And then there are weaker semantics for hardware that personally, I'm not a hardware specialist, but my personal belief is if your hardware gets so clever that your software can't use it without putting in lots and lots of synchronization, even though you can run little benchmarks that show fabulous performance for the things that you tested, this does not mean it's going to perform well at the higher level where we really need it to work. So total store order actually turns out to be a nice compromise. It's more efficient than sequential consistency, but strong enough to do the kinds of things we want. Because what it means is, if I got to that 5th word and I saw something based on a lock that had been set after I read the first word, the fact that I saw that means I'm also going to see all the stuff that happened before it. So I will see the new version of the first word, and therefore I will detect that something has changed and I have to do the work over again. Okay, so that's the basic idea of concurrency control. A mix. Writes are pessimistic. In other words, we take the lock first, but reads are optimistic. And that means, we just go ahead and do our stuff, and then we check at the end. If it wasn't right, we do it over again. And that was a new idea at the time that Eddie did this work. And it was complicated, not because of this basic technique, which in fact is pretty straightforward, but also there's a lot of other stuff going on these trees that I'm not going to talk about very much, but just one point. Supposing you're inserting a new key value pair into the tree. Well, you're reading. You read until you get down to that leaf node and you discover the key's not there. Well, you don't want to set locks. I mean, you're reading, so you're not gathering any locks as you go down that path. Now you get down to the bottom, and you have to modify that node. But modifying that node in many tree structures might mean there's no room in that leaf node, so we're going to have to split it. And if we split that leaf node, we might have to change the parent node. And so changes that happen at the bottom of the tree can percolate back up the tree. And so you could imagine handling this by taking the locks all the way down to the bottom, but that means you're holding those locks for sort of a very long time and on many things that are not going to change at all. So instead, we actually take locks going up from the base. And the reason it matters to have a discipline is that if you have the right discipline, you won't get any deadlocks. If everybody always locks going up from the bottom, this means they'll all be locking in the same order, and therefore we don't have to worry about deadlocks. Okay, and there's more details that I'm not going to go into, but that's the basic idea. We don't lock for reads. We have a way of making sure the reads are consistent, and then there's some extra stuff making sure that when we split the tree, we can make it work right. So no deadlocks. All right. So that was Mass Tree, and that's the system Eddie came to talk to me about, and it was an opportunity for me to learn a lot about how multi-core machines worked and what about concurrency control and so forth and so on. And, you know, we did talk about correctness for a while, but something happened which in retrospect is quite obvious, thinking from my perspective, which is I've always been very interested in transaction support in databases. I have very little interest in key value stores. There's a long history in systems of people who reject databases. They say, oh, those databases do way too much for my purposes. I'm just going to have a key value store. That'll be much cheaper. Then, you know, a little while later, they discover, oh, that really wasn't quite sufficient. So they make a little bit of a change to the database. And then they discover, I didn't quite have enough. You know, and the next thing you know, they're back to databases again. Databases have a lot of stuff going on in them that's very useful for applications, and particularly they support atomic transactions, which means that you can think about a concurrent program in terms of sequences of computations, and this reasoning process makes it much easier to reason about the correctness of your code. So, and you know, originally I said I thought databases in some sense were the killer app for multi-core computers. So here we saw, yeah, let's see whether we can do databases this way. So let's build on the ideas in Mass Tree, but turn it into a database system rather than a key value store. So one thing I forgot to mention, which is very important, is that the Mass Tree key value store sat entirely in primary memory. And so we went on and developed a database system called Silo. And like Mass Tree, the database sat entirely in primary memory. In other words, we did not worry about the problems that happen when the database gets too big to fit in primary memory. Now, primary memory on multi-core machines is gigantic these days. You know, I don't know what ours had. Anyway, very big. Okay, still not big enough that you can get away with worrying about without worrying about what happens if you overflow, but big enough for our purposes so that we could do this initial thing and focus on that part of the problem. And frankly, I believe that when systems get too big to fit on a single machine these days, probably you overflow to another machine. In other words, you use replicas to run read-only transactions in the past on old data, and you sort of keep your real state in primary memory. Anyway, this was just a way of sort of breaking up the work, so we didn't worry about that problem. We only worried about how do we make that stuff that's in memory run really well. We also made an assumption that transactions are what are called one-shot. In the original world of databases, people thought about somebody sitting at a computer interacting with a database, and they'd say, well, what about this? So they sort of go back and forth. They'd run something, the database would tell them an answer. They'd run a query, they'd get back an answer. They'd run a query, they'd get back an answer. Ultimately, they'd say commit. But in fact, the way databases are used today is people don't use the databases directly. They use them through applications. The applications run sessions where they interact with users. You know, like you're dealing with Amazon and they have your shopping cart. And these individual operations interactions that you do with a system like that are backed up by transactions, but they don't run transactions that span the entire user session. So this corresponds to what's going on in those applications where when the application needs to do something with the database, they run a transaction at that point just as a unit without any kind of interaction in between. So that's what's called one-shot requests. And then we did the obvious thing. Databases support tables. We implemented them as trees. They also have indexes. Those were also trees. And we had the cores working as workers. So if you think about a system like Amazon running on a multi-core, it's got many cores. Each core is managing sessions for many users, and that core is then interacting with the database on behalf of what it's doing for those users. And then the workers share the physical memory just as happened in mass tree. So there's a picture of a transaction just to make sure everybody sees what we're talking about. What happens in a transaction? You start the transaction, you might run a whole bunch of queries. They're basically using operations on the tree or multiple trees. And in the end, they either commit or abort. So the whole thing. So the big deal here is that mass tree supported individual atomic operations. You know, you could look up the value associated with a key, and then separately you might change it, something like that. But with transactions, you have to do a whole bunch of operations, and in the end, they all happen or none of them happens. Okay, so that gets us into the concurrency control issue, because mass tree is very efficient, but it only uses one object at a time. If necessary, it locks it, and then releases the lock at the end of the operation. Or maybe it didn't do any locking at all. So changing from that to transactions raises a question. One possibility is that we hold locks longer. And in fact, when databases first began, that's what everybody was doing. They were holding locks over long periods of time. The trouble with holding locks longer, there are two problems actually. The first one is the longer you hold locks, the more likely you are to conflict with other concurrent activity. The second problem is that when you start to talk about running transactions, there's no way of controlling the order in which things are used. And so different transactions will use objects in different orders, and this can lead to deadlocks. In database systems that use locks, they have very complicated deadlock control mechanisms to figure out what's going on and abort things if necessary. So the other alternative, and this was developed by Kung in the 1980s, I believe, is what's called optimistic concurrency control, where you don't use locks at all. Instead, you keep track of what's going on when the transaction runs. You keep track in the read set and the write set. The read set tells you what's been read. The write set tells you what's been written. And in the read set, you keep track of the version number of each thing that you read. Remember, in the stuff I showed you earlier, there was a version number sitting in the header word of each node and record. And in the write set, you store the new state. And then at the end of the transaction, you attempt a commit. Okay, and this is sometimes people talk about this as rather than asking for permission and then doing your work, you just go ahead and do your stuff and ask permission later on, and if necessary, you have to abort and do it over again, which is very similar to what was happening with reads in mass tree. Okay, so here's the commit protocol. Remember, so we have our read and our write set. So the first thing we do is we lock all the objects in the write set, and we may have to do some spinning in there if necessary. And this is actually bounded spinning. We don't sit there forever. Okay, after we've got all the objects that are going to be modified locked, then we check the version numbers of everything that's in the read set. So we look at all the objects that were read, and if their version numbers are the same, everything's great. If something's changed, we're going to have to abort the transaction. But notice this is very cache friendly, because if those objects have remained in your cache because nobody's disturbed them, they're just still sitting right there with the same version number, and everything's just lovely. After we've done those two steps, we have to choose a new version number for the objects. And we call that a transaction identifier. And the important point is that transaction identifier has to be big enough so that all future uses of that object will recognize it as being, different than what had ever been there before. And so we choose a transaction identifier that's one bigger than the version numbers of everything we read, including actually now the written objects, even if we didn't read them first. So we take all those version numbers, add one to them, and we're finished with that. This is all done locally in the core, so no use of any kind of global variable. Now we can update all the objects in the right set, and we store the new versions in there, and then finally, we can release all the locks, okay? So it's a pretty straightforward, extension of what was going on. Well, there's a whole bunch of other stuff going on in a database system that I'm not going to talk about today. Range queries are where you say, tell me all the patients of Dr. X or something like that. You look over a whole bunch of stuff in one tree as part of the query. Absent keys means I did a range query and it turned out that key 23 was not there. And if key 23 shows up afterwards, that really does mean you have to abort your transaction because you missed something. Persistence means what happens if there's a failure, how does my machine recover the data? And garbage collection, if you didn't collect garbage, after a while you wouldn't be able to do anything. So it turned out this performed very well. Okay, so this was really what the point of the whole thing was, and I'll get to that in a minute. What I'm showing you on this slide is I'm showing you the key value store, that's the pale line on the top, what we call mem silo, that's the system, our system running in primary memory, and you can see that the two lines track very closely. So we obtain the performance benefits of the key value store, even though we move to transactions. And this is using low-level, the YCSB benchmark, which is a low-level micro benchmark. The dotted line took memsilo, and instead of using that TID where we computed locally what it ought to be by just adding 1 to all the version numbers we saw, it had a counter. And so we had to read this global counter using, in fact, an increment, an instruction based in the hardware that allowed you to increment something by 1 in one instruction set, in one instruction. But that did not provide the same scalability as we were able to get by doing things the way we were doing it. Okay, the other thing that we looked at for performance was something called HStore. And what was interesting here was that this is what was going on in databases until we did this work. Mike Stonebreaker wrote a paper in which he basically said, we don't know how to get good performance on multicores for databases, so what we're going to do is we're going to split them up, we're going to partition them, and we're going to optimize for the system where each core only uses a single partition of the data most of the time. And if in fact we run into a transaction that needs to use multiple cores, then it's going to be more expensive. And everybody in the database world was working on this way of approaching databases. They had other techniques they were using, but that was the basic idea, all based on this idea that we could not possibly run a system like our system because it just wasn't going to work well. And what you see on this slide is the line sloping down is HStore. So what you see there is that, in fact, yes, HStore works beautifully when all your requests run in a single core. So you can see it's performing better than Silo in the case where there aren't very many cross-partition transactions. So if there are none, it's performing perfectly. But you don't have to go up very far. At 20% transactions, you're already starting to have degraded performance, and then it gets worse and worse and worse. So the idea of partitioning works really well if you're confident that you have a small number of cross-partition transactions. That requires very careful tuning of your system because you have to think carefully about how stuff is partitioned and who should be doing what and so forth. And the nice thing about Silo is that it scales perfectly. It doesn't get worse as you get multiple partition transactions. And the two lines there, one of them includes persistence and the other one doesn't. Okay. All right, so that was the work on Silo. And What was interesting about Silo in retrospect is that it changed the way people are building database systems. So since Silo came out, we've seen lots and lots of papers that, do this or that. So there's been papers that talk about, well, how do I, handle the problem if the database gets too big for primary memory, but I'm using a Silo-like approach. And there's even been work now on how do I run on a cluster of machines in a single data center using a Silo-like approach, but now I really have both multi-core machines and multiple machines in the cluster. But it sort of changed the way people build database systems. Okay, meanwhile, we went on, and the next step that happened is also obvious in retrospect, because as we were working on making Silo run, I began to think about data types. And I realized, seems to take a long time, data type, a tree is just a data type. And what we really had going on in Silo was we had a very clever implementation of a tree. We had a clever implementation of a tree, we had a clever implementation of a record. These are just data types, and so why should we treat this as a one-of? Why don't we instead turn it around and provide mechanisms so that programmers can design their own data types and use them in their own applications where maybe trees is not what they want. So that's how we moved to what we call STO, which stands for Software Transactional Objects. And what we're doing now is we're moving into the area of what's called software transactional memory. There's been a long stretch of work on the idea that you run transactions. That's the paper, anyway. All right. I think I had well, let me just talk about it. Anyway, there's been a long history of people working on programs run transactions. The underlying hardware or software is keeping track of every word they use and implementing the transactions under the covers so that when you say commit at the end, the system will decide whether you can commit or abort. And that's been going on for a long time, and it wasn't working all that well. The performance was not great. And what's happening here in STO is that we're saying, well, doing this at the level of words doesn't really make much sense because you don't understand, what that word is being used for. Maybe you don't need any concurrency control for that word, even though the software used it. Let's move up to objects and let the objects take care of the concurrency control, because there we can take advantage of the semantics of the objects. Okay, so STO, trees are an abstract data type, and the specification of the tree, or the specification of any abstract data type, has within it limits on the potential concurrency for running operations on those objects. In the case of trees, you only really care in the end if these two different transactions end up using the same record. And you might care that you want to make sure that if something gets added, it's used properly. But you don't really care about all the words that make up the nodes of the tree. Most of the time, all you really care about the record, and that record, really, you only care about the first word of the record because that's all you need to track in order to do the concurrency control right. And we can do all that in the software because we understand what's going on. It's a very old idea. You see, there's a paper here by Bill Weil in 1988 talking about how, with abstract data types, you can understand the semantics of the data and therefore get better performance. So with a data type, you have a specification, right? Everybody uses it according to the specification. The implementation is hidden and you can do all sorts of clever stuff down there. Okay, so the vision in software transactional menu is that applications run transactions, because it's well understood that it's actually much easier to write your applications if you can use transactions. Because as I mentioned before, you can think in terms of sequences of things, and that's a much easier reasoning regime. So they now in our system run transactions using these transaction-aware data types, and there can be many different kinds. Sets is what we were using in maps, is actually what we're using in STO, but you could have sets, you can have arrays, and so forth and so on. And so it's moving transactional memory up a level. And there's a picture of a transaction. This is an old chestnut always used to show you about what transactions are like in database systems. What I want to do is I want to withdraw some money from one account and put it into the second one. And I want in the end that either the transfer happened, so one account was decremented, the other one was incremented, or if that wasn't possible, I want to have no effect on the system whatsoever. So you can see that that's happening in here. I'm withdrawing money from account 1 and depositing it into account 2 as in a transaction, so either they'll both happen or neither will happen. Okay, so how did we do this? Well, we broke Silo into two parts. We have a platform now that supports transaction-aware data types, and then the implementations of the data types themselves. The platform provides what you need to run the transactions. So first of all, you interact with the transaction when you start the platform when you start the transaction, and we add a little bit of syntax to C++, which is the language we were using, so that we would know to make this call down to the platform to say, we're starting a new transaction. And then it provided state for the transaction in the form of those read and write sets that I mentioned before. And it provided an interface that allowed the transaction-aware data types to make the necessary calls to store whatever state it needed in the platform. And then it would use when it was time to commit, it would use a protocol implementing stuff. Okay, on the other hand, we have our transaction-aware data types, and they provide the operations you expect, like, you know, the maps that we're using have the operations that I showed you before to look up a value associated with a key, put a new key value pair in, and so forth. When you implement them, you record your reads and writes in the read set and the write set via operation calls on the platform. And then to handle the commit, you provide a bunch of operations and the platform does callbacks. So it calls them during the commit protocol. It's a very standard architecture for systems like this, where you call down to tell stuff to the lower level, and then it does something for you at the end, and it does calls up to let you get involved in whatever it is that's happening. Okay, so the callbacks are the one piece that is a little mysterious here, because it's kind of pretty obvious. I'm running a lookup, and so I need to put into the read set the fact that I read this record. But the callbacks are the thing I haven't talked about yet, so what are they? Well, transaction-aware data types provide the operations I have listed up there. They provide a lock to get the commit started. They provide an unlock for the end. They provide a check, which is what we were doing when we were checking to see whether any of the version numbers had changed. They do an install, which is what we were doing when we were putting the new values into the records. And then they provide a cleanup, which is something we didn't talk about before, but that operation is used for aborts, because if you made any modifications while you were running and then the transaction aborted, you have to make sure you undo whatever you did. But we also use cleanup after commit, because, for example, if you run a transaction that deletes a key value pair from a map, then you need to remove the key at the end. And the problem is you're using a tree, and the structure of the tree might have changed. So it's not obvious where the key needs to be deleted from. It may no longer be in the node where it was at the time you accessed it. And it would be expensive while holding all those locks to do the search for the key. So what we do instead, because it doesn't hurt the semantics, is we're lazy about it. We release all the locks, then we call after commit, and after commit can then get rid of the key. It searches down the tree to find it. So I'm not going to talk anymore about exactly what we did, and I'm going to show you some little performance results in a minute. We're almost finished, actually. But what I do want to do is talk about why are we getting good performance with this technique? Okay, because it turns out we're getting very good performance with this technique. And it turns out we now understand that the first thing we're getting good performance from, compared to other people's work, is that our read and write sets are very small. So remember I talked about transactional memory and how every word you tested, every word you used ended up in a read-or-write set. Here, we only put records, records as an object, not records as a whole bunch of words, but records as an object. Records go into there, but not the path to the record. So all the nodes along the path don't end up in the read set. And similarly, in the write set, we only have records, or maybe we have a leaf node if something was going on with it. Okay, so that was the main thing, but there actually are two other ways we get benefited performance. When I talked about how at the stage where we were checking whether the version numbers were equal, we do that by an upcall to a check method. And although what that check method could do is it could say, well, what's the version number now compared to what I saw before? But it doesn't have to do that. So it might be that all it does is it says, I don't care what it was before. So for example, in a car rental system, when you get to the end of the transaction, you don't care that there are still 10 cars left. All you care about is that that kind of car still exists. So you can use a relaxed check, something that's more permissive than looking at the version numbers, and so that reduces aborts because you have less possibility of having something that forces you to abort. And then the other place where you win is through the installs, which also involve computation. If you're using a number that's being incremented in your transaction, and you're not ever actually looking at the version of this number, and this is not unusual, sometimes you'll take a ticket, then you don't have to look at you don't have to lock that thing at all, and you can actually do the work of incrementing it at the end of the transaction. So some work you can just push to the commit part, and it saves you another kind of interaction with other transactions that would otherwise lead to conflicts. So we have several ways of avoiding conflicts. And I was just going to show you on this slide the latter two. So here in the withdraw operation, when I do the check, you see I only care that the balance is greater than the amount that I have right now. I don't care whether it's changed or not. So it would have been okay if there'd been another deposit into that account after I looked at it in the first part of the transaction. So that's a benefit of the check. Oops. And then for the install, what I'm showing you here is that, in fact, I don't even have to have the second account in my read set at all. It's in my write set. And I don't bother to do any checks. The checks don't matter at all. All that happens is at the commit point, then I add the amount to what the balance currently is. And these turn out to be important for certain applications because they avoid points of conflict. Okay, so I'm just going to close with a little bit of performance. Our goal going into Stowe was that we could do what Silo did without much loss in performance. Turned out we did better. Okay, so what you're seeing on this slide is you see Silo is always on the left as you're looking at it. And then we have several versions of Stowe. And Stowe Silo just uses trees. Of course, in databases, you like to have hash tables as well. And once you have Stowe, it's easy to add hash tables. They're just another abstract data type. So now we have Stowe with hash tables. And so that's the one, the purple one. And then the other two have to do with the checks and installs, what I was talking about, and how you can get away with fewer aborts by having these things that are more aware of the semantics of the transaction. Anyway, what you see is that, in general, we're doing better even with Stowe versus Silo. And then we get even better performance by adding some of this extra stuff. All right. And this is a regular parallel benchmark stamp. And the main thing here really is we're comparing now against, oh gosh, I've forgotten the name of it. I might have it on the next slide. Yeah, TL2, which was the best transactional memory concurrency control available at the time. It's doing much worse than we are. And when you get over to vacation, what you're seeing is the benefit of the checks that are done using software that's aware of the semantics as opposed to the raw checks. So anyway, the message is this technique actually works very well for certain applications. And it improves on what we were able to do with Silo because of the fact that we can take advantage of the semantics of the memory. We can easily add more data types if we need them. And also we can benefit from the fact that we have these transaction-aware checks and installs that take advantage of the semantics of the option. Okay, and I'm not going to really talk about this. We have compared with other techniques. The one that's most similar is this thing called boosting, which tried to surround sort of parallel data types with some semantics for transaction aware, and it did better than the raw stuff, but not nearly as well as we do. And that's really where I am. At present, what we're doing is we're looking, so there's an interesting question here. We get very good performance. So something changed. There was a rationale in databases that you shouldn't do things this way. We showed you could do it. And then we went on and added extra stuff to it. In other words, all this transaction-aware semantics. What is the best concurrency control mechanism for databases as they are today? And why is it that we're doing so well? And we're still looking into that. So that's one thing we're trying to sort of sort out. Another thing we're looking at is what we call two-phase transactions. It turns out that a very common paradigm is that you maybe look over a large set of stuff, and from this stuff you pull out a few things that are interesting, and then at the end you really only want to work on that stuff, the stuff that's interesting, and the rest of it doesn't matter. And you actually have a semantics for your transaction that explains why that other stuff doesn't matter. And we're looking into whether we can support that in a sort of a straightforward way. So that's my talk. Thank you.
Thank you, Barbara. Thank you, Barbara. Question time. Is there any question you want to make to Barbara? Here.
Thanks.
Hello. Welcome, if I haven't been able to say that, into university. And my question would be, if you have enough time, I don't know, perhaps about lazy replication, exploiting the semantics of distributed systems. I don't know if that deviates a lot from this topic. I don't know.
I don't think lazy replication, that would be a lot to get into. I think maybe, I mean, there is a whole other line of work I've done on replication. And Marta wanted me to talk about some of that. The most recent work, which I did with a student, Miguel Castro, in 2000, we published a paper in 2002 or 2003, is on something called Byzantine fault tolerance, which, for those of you who see this blockchain stuff that's going on, turns out to be, I mean, we really were dealing with the kind of malicious attacks that blockchains are worried about. And so there's a lot of work not being done by me. I've been ignoring blockchains, but trying to take advantage of those techniques to provide better performing ways of managing to get blockchains to have a single chain. Lazy replication is, stuff I did. We'd have to talk about that. I've almost forgotten lazy replication, because there was lazy replication, then there was something called view stamp replication, which is basically Paxos. That's the sort of standard, what you do when failures are only crashes. They're benign failures. And then there's Byzantine fault tolerance, which is the stuff I did with Miguel Castro in the late 2000s. It's not much related to this. But I am very interested in distributed computing still, and so I'm still thinking about what's the best way to perform stuff. So I haven't stopped being interested. I'm sort of thinking about blockchains, but it's a big world out there, and I'm not sure.
So at the beginning of your talk, you mentioned that the silo system is for one-shot transactions.
Mm-hmm.
But as you presented the commit protocol, I think it could be used for any other kind of transactions where the ones you mentioned, the user is interacting with the database and submitting one operation after the other, because in the Comet protocol, as far as I understood, what you check are the write sets and all this stuff. What is the limitation for this model? Is there any?
Yeah. No, you're absolutely right.
I understand that this is the model that is being used nowadays, but...
No, you're absolutely right, because there is nothing in the commit protocol or the read and write sets that I explained that rules out any kind of transaction. You're absolutely correct. It's just that, if you have these transactions that take a long time, what are called in the literature very long transactions, then the probability that when you get to the commit point, you'll actually be able to commit gets smaller and smaller and smaller. Yeah. And so it's not that there's a fundamental limitation here, it's just that, we were interested in performance, and that was the sort of performance we chose to focus on, performance for those kinds of systems.
Okay, and in the last slide, you mentioned this one with the figures with the scalability, number of threads, the previous one. What is the previous one? There is, sorry. Here, it looks like there is linear scalability when you move from 1 to 4 threads, but then the system is like it's not going up at the same pace, right? What is the limitation that is there that when you add, there are 16 threads and then you go to 24, the performance doesn't increase that much. What is the...
Yeah, so that there's an interesting question. So we had a machine with 24 threads, and you can see, what you really want here is you want a straight line right on the diagonal. That would represent perfect scalability. Now what you see when you look at this thing is that when you go from 16 threads, you're not getting perfect scalability. You can see that, right? And I would say nobody really understands what you need. The limits of this stuff is just not well understood. And even though you might show that something works up to 32 threads, that doesn't guarantee that it would work up to 64 threads, because at some point you reach a point where the conflicts just start to get in your way. And also, this technology doesn't work for every application, because if you have an application where there's just inherently lots and lots of conflicts, there's going to be conflicts and they're going to have problems. The thing that's nice about database systems, this is really a benefit of them, though nobody talks about it this way. They're big. There's a huge database. There are many concurrent users, but they're mostly not doing the same thing at all. And so you get a lot of benefit out of just making sure that you don't do false conflicts and that you have the right unit for your concurrency control and so forth. And I don't think anybody really understands how far you can push this stuff. Yeah.
Thank you.
Any other question?
Thank you very much for your great talk and for being here. I have a couple of curiosities. The first one is related to your approach to transactions. How that you mentioned you have been implemented in C++. So how does this relate to the ISO C++ technical specification on transactional memory that was published recently? So that is my first question. My second question has to do with precondition and postcondition checking. Should it be part of the transaction itself or not? Because if it is part of the transaction itself, it becomes an implementation detail. And otherwise, if you want to express in the interface, it does not fit very well in the model. So I never got a good solution for the second question.
Okay, and I'm not sure I can answer your question. First of all, I should say that I'm the sort of the abstract person in this team, and Eddie Kohler is a wonderful implementer. So we kind of divide up the work. And so I know something about, what TL2 is, and there's now Swiss TM and blah, 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 and I know some stuff about that. I don't know the ISO C++. C++ is not actually my language of choice.
I can imagine that.
But on the other hand, if you're working in systems, the implementation of a database system is very important, and you do need access to low-level features to get the stuff right. The second question you asked sounded to me like it had to do with constraints in database systems, but I'm not absolutely certain. And I tend to think about, one reason why it's nice to think about one-shot transactions is because you have a semantics for the transaction as a whole. And all you want at the end is that there's a sequential order for those operations, and you can reason about the semantics of the application at a very high level. And sometimes this allows you to avoid having to do some concurrency control and checking just because it comes right out of the semantics of the application. We're actually doing a similar thing in the objects. And so we're relying on the code to do the right thing. And when I talked about the two-phase transactions, again, I'm relying on the semantics. So I'm saying there's an explanation that tells me. So for example, what I meant there was I've got a bunch of red records, and after a while some of them turn blue. And once something turns blue, it never turns red again. And I'm only interested in the blue ones. So I look through everything to find the blue ones. And of course I touched all the red ones while I was doing this, but when I get to the second phase, I can forget all those red ones and only focus on the blue ones, and I'll still have a transaction. So I think, I'm not answering your question because I don't actually understand your question, but I'm saying you can get a tremendous benefit out of giving the programmer control when they understand the semantics. Of course, the downside is they don't understand the semantics. So there's some interesting papers in the database literature showing errors in code because the programmers tried to take shortcuts and turned out they didn't think about all the actual things and stuff like that. So I don't know the answer to that. There's some sort of, we'll work it out eventually.
Neither do I. Thank you very much.
You're welcome. Okay.
One last question, because Barbara has to take a train in a couple of hours, so.
Okay, just a quick question.
Sorry.
All the benchmark is show up, from my understanding, are from basically a single machine. Did you ever try, because you talk about big data center, to benchmark this on multiple machines? Because I think when you show up the H-stroke comparison, but it's based more on partitioning data, how good or bad is silo when you have to fetch data through the network, basically? Thanks.
Okay, so thanks for asking that question. I haven't done work on this, but Miguel Castro, who is the very same student I mentioned who did the Byzantine fault tolerance, now works for Microsoft Research, and he has built a cluster system where basically he's implementing silo using, I can't remember the name of the new way that you access remote memory in such a system and so forth. It actually scales very well. And it's an area I am very interested in, but I haven't done any work in it myself. However, what I can say is this approach does seem to be able to scale up to that kind of a setting.
Okay, thank you.
Yeah.
Thank you, Barbara.
You're welcome.